Alrighty, hello everybody. This is Mikey. As we go through this, I hope that this will answer a few of the questions that we have on Chapter 8. I do apologize for not being able to get through everything today in class. It hit me pretty suddenly that there are a lot of things that I have to go through, and I thought it'd be better spent if we can just practice a little bit more in this video and go through the reagents to get a better understanding of what the real wheel of opportunity is. So I've gone through and made a chart, and we're going to go through all the practice problems that we had from today in class, just to give you guys a better understanding of the reactions and the mechanisms. So here we have the wheel of opportunity. Other people call it the wheel of doom, and you guys are probably getting a little bit of an understanding of why they call it the wheel of doom. Brother Johnson, being as optimistic as he is, he calls it the wheel of opportunity. I love that. I think it's great. He's awesome. So as we go through the wheel of opportunity, I've made this and I've turned this into a chart form, but you'll see here that I've numbered 1, 2, 3, but then it kind of skips around a little bit. That'll play into what I've categorized everything on the chart. So I recommend that you take a screenshot here to kind of compare. If you're used to looking at the wheel of opportunity, I know many that study this, that they love it. And for me, I love charts, and so I've turned the wheel of opportunity and the resource that they've given us here into a chart that helps me better study. And if you work that way, hopefully this video is helpful. If not, please keep using the wheel of opportunity. It's a great resource. All right, so going into the chart that I've made, I will let you take a second to take a screenshot of this. You can take a screenshot of this as well. All right, one more screenshot. Alrighty. So I'm going to go through each of these reagents and reactions and kind of just talk about how they're used, and then I will go into the mechanisms and the questions that we provided in class today. But just kind of breaking down what I call the chart of happiness, which goes hand in hand with the wheel of opportunity. In the chart of happiness here, we have just a couple of columns, and column 1 is called numbers. We go over names, reagents, products. We go over whether or not each type of reaction is a Markovnikov or anti-Markovnikov addition. We go over whether or not they are syn or anti-addition, and we go over whether or not we need their mechanisms. So this is kind of just an easier way to organize it in terms of everything. It's a little more encompassing, or all-encompassing. I recommend too, there's probably things I'm leaving out. This is made right after class, but and so maybe I haven't thought of something. I recommend you make your own chart or make your own graph, or however you like to study. This is just an example of what I've done in order to help study more for this test. Alrighty, so looking at the chart of happiness key real quick, we can see that the asterisk that's above products is related to this right here. I'll draw that arrow better. So that asterisk just shows that we are taking our products from the reactant of this alkene. It's an alkene connected to an R group. So that is what we're working with. The check mark means of course or yes. That has to do, and the X, the red X means no. That has to do with the relationship between whether or not we need to know our mechanisms. So green check mark means yes. Red X means no, we do not need another mechanism. NA you'll see between Markovnikov and anti-Markovnikov versus syn addition and anti-addition. That just shows us that it's not really applicable to think of it in that way. I think a tendency is actually we see syn where there's syn addition or anti-addition where there's not Markovnikov or anti-Markovnikov, which is kind of cool. There are occasions though where it's both. So you can see right there. All right, let's keep going. So you see here that the blue or the purple M is Markovnikov and the orangish red is anti-Markovnikov. This just has to do with the Markovnikov addition, anti-Markovnikov addition, which means Markovnikov we add something. It's the addition of something onto an alkene at the more substituted position. And then the anti-Markovnikov is an addition of some kind of molecule onto the less substituted. So there's less carbons attached to the area where less carbons. I say less carbons, but it really less molecules attached to the end of the alkene, and there's more hydrogens instead. So there's less hydrogens in the Markovnikov addition, and more hydrogens on the location where it's added on the anti-Markovnikov addition. All right, let's dive into it. I'm not sure how long this video is going to be. I'm just going to record it in one sitting. You're welcome to watch it on ×2 speed. I don't really care, but I hope this will help. I really do. If you have any questions, please just email me. Send me a message on Canvas. It'll do the same. Some of you have my number. Actually, I think I gave my number out, so you're welcome to text me too. All right, so looking at each of these, like I said earlier, I gave each of these reactions a number in relation to the wheel of opportunity. I recommend that you go back and screenshot that if you already didn't to compare it. The first reaction here that we're going to look at is a catalytic hydrogenation, which you can kind of break down that word, hydrogenation. You just add 2 hydrogens using the catalyst of nickel. That'll get you from an alkene to an alkane by adding 1 more hydrogen on an area where there's already a hydrogen. So you can see in this alkane up here in the top right corner, alkene on the top right corner, there would be a hydrogen, there would be 1 hydrogen on the carbon at the top, and then 2 hydrogens on the primary carbon, and then we would add a hydrogen to the primary carbon and the secondary carbon there. I hope that makes sense. All right, so this reaction is not really involved with Markovnikov or anti-Markovnikov, but this reaction is involved in syn addition, which means that this molecule, when you put something that will add hydrogens above or below this molecule, it'll add hydrogens on the same side, or it'll add it by syn addition. That's important to know. Does this involve a mechanism we need to know? No, don't worry about it. All right, so number 2 is, I want to break down this word again, alkene hydrohalogenation. Hydro meaning H, halogenation meaning X, or a halogen. So halogen, halide, whatever you want to say, this halogen and this hydrogen will react with an alkene in order to add a hydrogen, and on the less substituted position, it will also add a halogen on the more substituted position by Markovnikov addition. So this takes the Markovnikov addition approach, and we'll see in nature that HX will actually add a hydrogen. I say HX, but the halogen will be added onto the more substituted carbon. We do need to know the mechanism for that. We will go over that in this video. All right, looking at number 3, we go over halogenation. So this is just halogenation, which involves 2 halogens. It'll add halogens to either side of the alkene. So this halogen 2, right, this X2 will add 2 X's to either side of this alkene, and that's kind of helpful. Therefore, we're adding the same molecule to both sides. So really, Markovnikov isn't really that important here. We do want to say though that this molecule will add halogens on opposite sides. So it'll add it by anti-addition. So really, like this halogen will add from the back, or this halogen will add from the front, or vice versa, depending on the orientation of the molecule. But you'll get, basically, I can even draw it here to better represent what I'm saying. I'll draw a wedge and a dash here. It'll add like this. Hopefully that makes sense. We will need to know this mechanism. We will go over it. Number 4, right here, we're going to go over number 4 molecule of number 4 reaction. This is halohydrin formation from an alkene. So a halohydrin formation. We know this involves both hydrogen and halides, and this involves H2O specifically, and a halogen gas, basically. I guess not halogen gas, but it had two halogens. I believe that the title that may be used in class involves water. That's actually probably a better name for this. You can go back and look at that, but this one involves water. So the difference between this one, number 3, and number 4, are that halogenation involves just X2, and halohydrin formation involves X2 and H2O. This is where we see a halogen added to the primary position, and we will get our OH, our alcohol, added to our more substituted position. Again, this will be added by anti-addition. In stereochemistry, understanding stereochemistry a little will help us to understand that if there's something bulky in the way, it's going to add on to the other side naturally, or it's going to push something to want to move away from the molecule that's being added. So that's why when you throw on this hydrogen or this halogen here, it'll push the OH away to the other side of where the halogen's pointing, thus making it anti. We will need to know the mechanism for this. We'll go over that again. So number 5 is a acid catalyzed hydration of an alkene. You can think acid catalyzed hydration. Hydration typically meaning something to do with like with hydrogen in the first place. Hydration meaning H2O or water. Acid catalyzed, we can think H2SO4. And when you combine these two, we're going to go over this in the mechanism, but when you combine these two in a solution, generally the acid that we're working with isn't actually H2SO4, it's going to be H3O. So I'll show you what that means in a bit. All right, so this product ends up forming or adding a hydroxyl group on the more substituted carbon of our alkene, of our original alkene. And this adds by Markovnikov addition because of that, or I guess that's the concept of adding by Markovnikov addition. There is no syn or anti for this. It's not applicable. We will need to know the mechanism. Moving on to the next sheet. Number 6, we have oxymercuration. Oxymercuration involves not that. I was reading this. I'm like, that's not oxymercuration. One second. Let me edit this. All right. So for those of you who took a screenshot of this, I am so sorry. I've already 13 minutes into this video. I'm not going to stop it. But take a screenshot of that. Get a new screenshot. Go delete the old one, please. I forgot. I switched those around and I forgot to change the reagents. So moving on, oxymercuration involves this reagent here. I'm going to zoom in so you can see that a little better. Basically, you can think oxymercuration, Hg right here, if we remember from our Gen Chem days, Hg on the periodic table is just mercury. So the biggest player in here you can kind of think of is our OH here, I guess, and in our H2O. We do not need to know the mechanism for this, so I won't go any deeper into that. Just like our last acid catalyzed hydration of an alkene, this molecule will add a hydroxyl group onto the more substituted carbon, but there are no shifts that will happen within this reaction. So no shifts will happen. This adds by Markovnikov addition again, and they're not applicable when it comes to syn and anti-addition. Again, no mechanism. Number 7, we have our hydroboration oxidation. And this is our first step involving BH3 and THF, and then H2O2 and NaOH as our second step. this will form an alkene into a primary, well, it'll place a primary hydroxyl group onto this alkene and add a hydrogen onto the more substituted carbon. So this concept is the addition of a molecule by anti-Markovnikov, the anti-Markovnikov addition, I should say, and this is one of those that involves both syn addition and anti-addition. They will be added from the same side. So I might need to confirm that with Brother Johnson. Just if there's a complication there, just let him know. Mechanism, you don't need to know. No worries about it. Okie dokie. So when it comes to number 8, this is called an alkene epoxidation. So making epoxides. This is an epoxidation. So this is something, I'm going to zoom in here so we don't, so we can see this. You're going to see on your sheet that says peroxyacetic acid. That's great. You're going to need to know the actual structure of peroxyacetic acid for your for this reaction to work. And also acetic acid, we'll come to find, is just this. So this is acetic acid. I'll write that A and A. And that's peroxyacetic acid. So know those in order to know your mechanism, and you'll be sitting pretty. Okay, the product of this will form this cute little triangle there with an oxygen on the end. Where the alkene used to be right here will then be an epoxy group right there with an oxygen connecting to both sides of that original alkene. No need to worry about Markovnikov or anti-Markovnikov. This will go by syn addition. So you can see, we'll see in our mechanism that really it'll look more like this, and the epoxide will be coming out towards us. It's kind of a triangle. You can't really get, you can't really look. The triangle will go one direction. All right, know the mechanism for that. All right, number 9. This is a dehydration of alkenes. The important one to remember for this one is OSO4. For some reason, I like to picture this as a bear, and I think in Spanish, oso is bear. This kind of looks like an upside down bear, I guess, with the H's being, like the O's being his feet and the H's being his claws. I don't really know. I could draw a little bear for you guys, but it's probably going to look really bad. Basically just an upside down bear with his claws. Yeah. Anyways, so that's what I like to think of the dehydration of alkenes. OSO4 ends up putting two hydroxyls, hydroxyl groups by syn addition onto the alkene, removing the alkene and forming those bonds. Again, by syn addition. You do not need to know the mechanism for this. It's pretty complicated. All right, number 10 is ozonolysis. You can think ozone layer, which is just O3. So the first step is O3, and the second step is throwing on zinc and H2O. Again, another complicated mechanism we do not need to know. Syn, anti, doesn't matter. Markovnikov, anti-Markovnikov, doesn't matter. Why? Because the product actually just takes an alkene and cuts it in half. So it cuts it in half, and on both sides that are cut in half, it puts an oxygen on it. So it forms, I mean, basically, this could be an aldehyde and some kind of a carbonyl here, or not an aldehyde, sorry. Acetone, my bad, and then an aldehyde here. Right there, aldehyde. Okay, hopefully that helps a little bit. Anyways, O3, the ozone layer. You can think of it, the ozone layer, and the concept of creating holes in the ozone layer. It creates a hole in the middle of this alkane here, and then adds oxygens to it. So there you go. We have 3 more, and then we'll move on to our mechanisms. So in the chart of happiness, we find these 3 more. This 13th here, right there, is something that we've added, Brother Johnson added, in order to help us understand a little bit better the one from chapter 9, I believe. We'll go over that mechanism as well, so I won't cover this one much here. But looking at number 11, we have hydrobromination of an alkene with peroxide. Pretty self-explanatory. Hydrobromination with peroxides. This hydrobromination of an alkene with peroxides will add a halogenation or a halogen onto the less substituted carbon, thus making it an anti-Markovnikov addition. No need to worry about sin and anti addition there. And we will need to know this mechanism. Again, like a record, I will say that we're gonna work on that. Number 12 is a polymerization using. I wrote this specifically using peroxides. All we use for this is actually just a peroxide. You'll throw in peroxide onto a hydrocarbon chain, and this is actually how they make something called PVC. This is how you make PVC pipe. And you'll actually make that hardened substance. You'll melt it back down, and then you can shape it into a pipe and use it in your plumbing. Super awesome. So this right here doesn't matter when it comes to Markovnikov, anti-Markovnikov, sin, and anti. We will need to know the mechanism. All right, quickly from number 13, the addition of an alkyl halide to alkyne. This is basically you take an alkyne right here. You can see, I'll zoom in here so you can see it better. From an alkyne, you will have a hydrogen sticking out on the end of the alkyne. I'll try to draw that better. So this is the carbon right here. This is a carbon right here. And this is a hydrogen sticking off of it. Essentially, this reaction will pull the hydrogen off, leave the electrons there with a formal negative charge, and then take something else and connect it to take another hydrocarbon and slap it on to be able to make a bigger molecule. So, alrighty. And I didn't really go much into the polymerization. We'll go into that in the mechanism. So moving on, we are 23 minutes in. So draw the mechanism for the following reactions. What I'm going to do here is just go through each of these and kind of explain along the way. We did review some of these in class, the first 3 or 4. Not really so much with the 3 and 4 there, unfortunately, but I hope to make it up to you guys here. So talking about this, right here we have this molecule and hydrogen bromide there. I actually recommend you guys pause the video and try to work these out on your own, and then I'll start going into it. All right, so looking at this, we are going to start with our, what is this, a 1, 2, 3, 4, 5, this pentane group with an alkene on it and 2 methyls. We will have hydrogen connected to bromine here, and I will draw their electrons. The electrons from this double bond, or this from this alkene, I should say, will reach out to grab the hydrogens off of this hydrogen bromide, and that will push the hydrogens from connecting hydrogen to bromine there back onto the bromine. So that'll move us to our next step, where we see, that's not right. where we see a carbocation form and a hydrogen ends up being attached. But the question is, which side does it attach? Does it attach here? Does it attach there? Well, in a normal situation, you would say that it attaches to wherever is least substituted, so we can put the bigger molecule on the more substituted area, and that's what our product is showing. So it's important in organic chemistry. You might be asked to do something, and then they ask you to show a specific product. I believe it was asked in class today, what if we're not given the product? For the most part, you're going to want to draw the major product, and you can welcome to draw minor products. Usually it'll be specified, though. They'll ask you for major and minor products. For the most part, we're going to draw our major products, which this would be, I believe, our major product. So, looking at this molecule here, we are going to say that this hydrogen then would have to add to, and I'll make this red to make it more understandable. We'll add to the carbon that's further away from the 3 methyl groups, or I guess the 2 methyl groups on our chain. And this will leave our bromine out here with a formal negative charge. Whoop. And here we have our positive charge. So this isn't the most stable that this molecule can be, and this is an important key point that I made in class today. When you have a carbocation in a reaction, and it's definitely not the product that they're wanting, if you're wanting to still continue the product, to the product, you're going to have to look at the product and make a determination there. With the carbocation, always look for 1,2-methyl shifts or 1,2 hydride shifts. In this case, we can make the most of our shifts by moving a methyl group. Let's not erase that, actually. Let's just draw it. So moving a methyl group from here to there, which will allow us to build a molecule that looks a little bit more like what we're looking at in our product. We'll move our carbocation to be more stable on this tertiary carbon. I'm not going to draw the hydrogens anymore, but they're still there. And we still have our poor little bromine ion out here. And then we're going to attach this guy. The electrons are going to reach out and connect to this tertiary carbon in order to fill that gap and thus get us our product. There we go. And that is how the mechanism will run. So first, the mechanism is going to reach out, grab the hydrogen. Any shifts that need to happen will happen, and then it'll reach out and grab a bromine and put it in the more substituted position. I sound like a college student there, subsidized. Okay, yeah, and that's about it. So if you have any questions, let me know. And our tutors are available, as well as Brother Johnson. So we're going through this as well. Let's look at this reaction. This is let's actually look back at our chart. What is this called? This is called our hydrobromination of alkene with peroxides. So let's do a hydrobromination of alkene with our peroxides. This is going to be a free radical type of mechanism. It's going to look a lot like our free radical mechanism. A free radical mechanism. So we are going to start with our initiation step, where we take peroxide and we split it. I'll do what was drawn on the board today and number these. And I'll draw our little electrons. I draw the arrows usually with red. Sometimes I don't, but I try. So these arrows, important to know. These arrows right here show an arrow with an arrow. The red arrows that I drew here are only half arrows, which show the movement of one electron. The other electron will actually, so this one bond is made up of 2 electrons, and 1 electron will go to this right oxygen, and 1 electron will go to this left oxygen, thus giving us 2 different ROs. All right, hopefully that makes sense. So we take one of those ROs, in our second step of initiation. It's a radical, by the way. This RO radical. Add it to hydrogen bromide. Oop, I just erased that. Let's see. Okay. So this bond will split here, and this radical will reach out and attach to this radical, bringing the hydrogen over to the R to make ROH, or over to the O to make ROH, and leave us with a bromine radical. Alrighty. Moving on to our propagation steps, we have a cyclohexane with a pentane and an alkene on the end of it. Here we're going to throw on, let's do 2 steps like we did in the first part. So a total really of 4 steps here. We're going to throw on our bromine radical from the first or the second step in initiation and attach it to this guy by doing the sort of same thing. We take this double bond and split up its electrons. And this will move it, I actually don't need to draw a plus here. And this will move it to this, the end of the hydrocarbon chain. Why, you ask? Because a radical on the end, say if our bromine was where the radical was, and the radical was where the bromine was, a radical on the end is not as stable, not as many resonance abilities as a radical that is stabilized by more carbons. Alrighty, so we take that result. That was a wonky looking cyclohexane, but I'm glad that it saved it. So we take that result. Oh, and I should add two. Oh yeah, that's good. We take that result and we will react it with another hydrogen bromide. To do the same thing. And this kind of just makes a reaction that just keeps going until we get to our termination step, which we're not really expected to really say, because there's not many of those reactions that actually happen. Once the reaction finally is depleted, at the very end, the last one reacts in a termination step, and then that's not going to happen very often in terms of percentage. So we see here that this hydrogen and this bromine bond here is broken up into two different electrons. We have these electrons reach out from the radical to connect along with the hydrogen, and the other electron will move on to the bromine, thus forming our desired product. Oh, one more. And another bromine radical. All right, hopefully that answers your questions. Again, let me know if you have any more. 33 minutes in, let's keep going. All right, so talking about this mechanism. This mechanism involves H2SO4 and H2O. This is our acid catalyzed hydration. Let me just double check that. Acid catalyzed hydration, yes, of an alkene. See, I haven't memorized these, but anyways, so let's start with this. I'll draw this out, but first I want to explain something like I did earlier when I was talking about the reagents. So important to note that this H2O and this H2SO4 is actually going to react in order to form, well, I'll do this, react in order to form more H3O plus and HSO4 minus. So when you throw in water and H2SO4 into a vat, the one that's actually the acid is more likely to be hydronium than H2SO4, and that's the one we're going to be looking at in this reaction. So when you see H2O and H2SO4, just know you're going to be working with water and H3O. So, all right. On that note, let's get into it, talking about how this hydronium ion will actually will donate one of its protons, acting like an acid, or acting as an acid. It'll donate one of these protons by these electrons reaching out, grabbing a proton, and pushing the electrons that it was connected to onto the oxygen. This will get us to our product. Oh, also too. I'll stop there. If you didn't take a picture before and try to work these out on your own, please do. A lot better to try these out on your own to see where you went wrong. If you did, before you try to just watch me do it. So it'll help you with your understanding about the nature of the movement of electrons and molecules. So this will form not an alkene, rather a carbocation. So this carbocation will form really an either position, because it doesn't matter. It's the same either way. And we're just going to now say that we have H2O from that hydronium ion. And it's important to note that these actually also have hydrogens. What was our thing from earlier? Where we have a carbocation, we will see a methyl or a hydride shift. So which one will occur? A methyl shift or a hydride shift? Think about that. All right, so what will actually happen is a hydride shift. If we were just to move the methyl shift, it really wouldn't fix our problem about a less stable carbocation. So for that purpose, we're actually just going to throw a hydrogen over there to move the carbocation onto our, I'll do this, to move a carbocation onto a more stable position. So this is going to be a 1,2 hydride shift. All right, this 1,2 hydride shift gives us a carbocation on the tertiary carbon position. And the rest of it is satisfied at that point. Now we have water that's hanging out in the ethosphere here. Water is going to come and attach itself to that tertiary position. Let's go up. And form a positive charge, a formal positive charge, because oxygen is now connected to too many things. What will happen at that point is that we take another water in order to form our hydronium ion again. It will reach out, grab hydrogen, and move onto the oxygen. And what will that get us? Our product. So that is what happens with H2SO4 and H2O. What will happen is the hydronium ion will donate a proton. It'll form a carbocation of some sort. If it does, awesome. You'll have some kind of shift if you do form a carbocation. Water will attach to that carbon in need of stabilization. And then another water will actually detach or deprotonate the water that's attached to the molecule now in order to give you a hydroxyl group, and that gives us our product. Again, important to note, always look at your product to determine where you're going. You don't look down in order to know where you're walking to, you look forward. So look at this in order to know which direction you should take your mechanism. All right, looking at this one, pretty simple, but I was talking about earlier with peroxyacetic acid. I myself had to remind myself, I don't even remember what peroxyacetic acid looks like. You can actually dissect it by looking at the word, and if you know the etymology behind peroxy, peroxy and acetic acid, you can kind of dissect it. But let's get into it. So peroxyacetic acid, PAA, you'll see it sometimes abbreviated as, is actually drawn like this. And I'll draw the extra hydrogen there. All right, so that's shown like that. I'll draw its little electrons. Okay, so PAA is shown like that. Acetic acid will show in a bit. It's just what's left over in the end of the day. When it comes to different things that are left over in a reaction, it's important to put any subproducts that involve carbons, given that this is organic chemistry. Sometimes some teachers won't have you really put different byproducts that are created if there's not really anything organic involved in it. But definitely with this one, you have 2 carbons. You're going to want to include acetic acid or peroxyacetic acid in your mechanism. We're really acetic acid as the end result from this reaction. Let's dive into it. All right. So remember that this reaction has specifications, and we can go look back at our chart. So the peroxyacetic acid was over here. It is syn addition. So let's make sure that we remember that with syn addition. We have this molecule right here. And all of these are, my question was, okay, well, actually, sorry, let's not go into that just yet. I want to make note before I get too deep that this right here and this right here are sp2 and sp2 hybridized carbons, therefore making it trigonal planar. It's flat in layman's terms. sp2, there's only 3 things connecting to each of those carbons. There's another hydrogen right here. Because of that makes it, that sets its orbitals in sp2, which is helpful for syn addition because we can add things to the same side, and it's going to be a pretty flat surface to do so on. That's the point I wanted to make with that. All right, so drawing peroxyacetic acid, let me move this out of the way real quick so I can grab this and move it down here. I'm just going to draw PAA down there. Okay. So showing what happens here, I always like to start from this, but this reaction from this double bond here, but this reaction is a concerted mechanism. So this concerted mechanism means that everything happens at the same time. So really you can start anywhere as long as the chain is correct. So I like to start from the double bond. The double bond will reach out, these electrons will grab this hydrogen and force the electrons that are on this hydrogen to oxygen to reach out and attach to this stable tertiary carbon position on the side of the alkene. This part, or the double bond will reach out and grab this specific oxygen here, attaching to that, and then will force these bonds down to the oxygen carbon connection, forming a double bond. We can see here in our product looking forward that we have 2 different things that we need to solve for. So we know now that there are 2 different pathways we have to diagram, and knowing that this is syn addition and that this is flat right here, this means that it could probably add from the top and it can add from the bottom of the molecule. It's flat, kind of like this. If you were to think about it this way, it could either add from this way or this way. And if you added from the bottom, it would push the methyl group up. If you added from the top, it would push the methyl group down. If you were to turn it back towards us this way, you would get, you would get what we see right here. Hopefully that makes sense. So top attack and bottom attack. Know that also too, when you're solving these kind of mechanisms, you might not be given the products, but you should be expected to know that there are multiple products, especially if they say products plural. A key thing to remember is that achiral, let me plug in my tablet, achiral plus achiral molecules, so two achiral molecules, this one and this one, will equal a racemic mixture, which means that there are multiple products, usually split 50-50. All right, so with that knowledge, let's go into it and talk about, let me just copy and paste this. That'd be a lot easier. Copy, paste. Copy, paste. Okay. So we know that this oxygen right here, this bond and this bond, maybe I shouldn't do dots. This bond and this bond are then connected to where the alkene was. We've got to determine if it was added to the top or added to the bottom. If it was added to the top, then we know that it'll push the methyl group down. Let's draw it differently so we can actually see it'll push the methyl group down, and these will be pointing out towards us being added from the top. Or you could say the front. Let's say top or front, or bottom or back. I like to say top and bottom just because of the method that I showed you earlier about looking at it like as if it were flat, like a piece of paper on a desk. All right, and then the opposite would happen here, where this methyl group would be pointing out towards us if it was added toward the bottom. Maybe to get that, we'd have 50% of this and 50% of that. Okay, perfect. Hopefully that makes sense. I don't think there's anything else there I need to cover. Let's move on. Okay, this was the stuff that we didn't really get to in class today. I recommend that you take a picture of it and then you attempt to solve it on your own. These ones are pretty complicated from here on out, so it's a-okay if you have to look at the video, but do so to try to test yourself, quiz yourself what you do and don't know, and then compare and pick apart what you don't know in order to know what you do know and to learn. All right. So talking about this is our halogenation and hydrogenation at the same time. So this would be like a halohydrin. Let's see if I was correct. So halohydrin formation from alkene, that is correct. Oh, let's review actually. Sorry, it's probably going to give you a migraine looking at this going so fast. We remember that halohydrin formation forms an oxygen on the more substituted position and adds the halogen onto the less substituted position by anti-addition. So let's go into it. All right, looking at all of this, if we were to draw out our that's the cyclohexane. If we were to draw out our cyclopentane group, there we go. We have our chlorine here. This is another concerted mechanism, so it really doesn't matter where you start. I should start from the double bond going to the chlorine, and then these electrons go to the carbon on the other side of the alkene, and the rest of the electrons go to the other chlorine. Now this is also trigonal planar again. We have an achiral molecule and another achiral molecule. I can't spell achiral molecule, which means that we're going to get a racemic mixture. Woohoo! That was cringe. I wish I could edit that out. Anyways, so we'll get two different reactions. And our products also tell us that too. That's kind of nice. All right. So we can show here that just like in the one previous, we're going to have chlorine in two different ways attached to this molecule and detached from the other chlorine. So it's going to be from the top or the bottom because it's flat, pushing the other methyl group down. So let's draw that. Cl, and this says too many connections there for what that chlorine wants, and so we're going to draw a plus sign. A positive charge, I should say. And then there's going to be another chlorine ion there. Okay. And then I'll just draw that on the bottom side as well. So this is attacking from the top. This is attacking from the bottom. It'll push the methyl group up, and the chlorine will be on the bottom. So far away from us, so sad. All right. Now we're going to take the H2O part of this and throw it on. And this guy's going to come in and attack from the back here, pushing the chlorine or the electrons onto the chlorine. Same thing up here. I'll draw that up here. Sorry, I'm kind of doing this at the same time. These are both different ways that this could happen. The oxygen will want to connect to the area where there's most, where it can be most stable, and its electrons can be shared the best. It'll push off the chlorine that wants electrons because of that positive charge onto the chlorine, and then we will get the same molecule, except now chlorine will just be alone over here. And we will have attached, it'll actually push down this methyl group, my bad. You know what I did? Sorry. I think this was actually, I drew out top and bottom, but I started doing bottom and top. So this will go above the molecule, push down the methyl group, and then pop off the bond to the chlorine and push the electrons onto the chlorine. And then this will have a positive charge right here. The same thing will happen where H2O will come and take one of the hydrogens off and push it back onto, let me draw those electrons, push it back onto the oxygen, thus forming this product. It's really bad arrows, I'm sorry. This one's a little sloppy. Anyways, and then this one, the bottom attack, will come up from the bottom, push up the methyl group, push off the electrons onto the chloride atom, and you will have an H2O group that is attacked by more water. And turned into this product. It's a little messy. Feel free to take a screenshot of that and practice that. But essentially the same as the one before. It's a little different, involving more elements. The next one's even worse. So, not worse, but there is a little bit more of conceptual understanding there. So going into this, same sort of deal. We have our halogenation reaction. Looking at our chart, I don't remember what number that is, but you can go back and look. I've got to wrap up this video. I don't want you guys having to look through an hour's worth of videos, but that probably is going to end up being the case. You are totally welcome to watch this times 2 speed. Say 30 minutes hopefully will be super helpful to cover a week's worth of material. All right. So let's go through and, oh, hang on. So this is another concerted mechanism where our electrons will come and grab onto this bad boy right here, the bromine. The electrons from the bromine will attach to this carbon right here on the other side of the alkene, and the rest of these electrons will get pushed off onto this other bromine. So we see that two achiral molecules make a racemic mixture. So we're going to form a top and a bottom attack, as we can see also in our products. So the top attack will end up looking like this. And same sort of deal, it has a formal charge. Okay. And then we will have a bromine ion there. Okay. So we can see here that we have two different bromines attached to this. Obviously, this looks like anti-addition, and I'd imagine that's what the addition is. So we can see that this is a top attack from the bromine, and this is a bottom attack. Sorry, pause right there real quick. Making sure we go onto, I was actually correct in saying that this is a top and this is a bottom. Looking later on, this ends up attacking from the bottom position. Sorry, from the top position. And this ends up attacking from the bottom position, but the chlorine itself actually attacks from the top and the bottom. That's what this is saying. I apologize. Okay, so attacking from the top and attacking from the bottom. All right, so the bromine attacks from the top and forms that epoxide-looking type of reaction there. And let's see. This bromine will then come around from the bottom. Here, let's do this. We'll come to the bottom of this and attack, because if you were to picture this on a more flat scale, this is supposed to be a hexane. These are pointed, oh, it's getting late. These are pointed this way, up like this. So there's not really a whole lot of room for this little bromine right here. He's like so sad. There's not really a lot of room here to join his friend group. But if he were to go on the bottom, he could work his way up the food chain when it comes to popularity in the bromine group. Anyways, so he attacks from the bottom because there's more room to fit in there, and this will form our I'll just write the product. This will form our product right here. Awesome. Same thing will happen if our bromine is on the bottom here. And the bromine ion will attach from the top. attack from the top. Ah. Well, let's see. Really doesn't matter where they attack from, because it'll end up with the same type of mixture. All right, and I should have colored this red. Boom, haha. Can't get me for that. All right, and there's our reaction. Pretty simple. Splits apart, I guess, a concerted mechanism in a 2A chiral molecules form a racemic mixture of a top and a bottom reaction. The other part of the halogen will attack from the top or the bottom, depending on the orientation, and get our products. All right, this is the last set of mechanisms to work with. Woohoo! You've made it through an hour and 44 minutes of this video. Holy cow. Or maybe I should say I've made it through an hour and 44 minutes of this video. Let's go through this real quick and talk about this. I want to add one more thing before I do that, though. This is by anti-addition, just to clarify, just to make sure you guys remember. All of these are added by anti-addition. So, sorry, not all of these. When I say all of these, it's very vague. This is a mechanism. This arrow right here represents an anti-addition. This arrow represents an anti-addition. And this arrow represents an anti-addition. And this arrow represents an anti-addition. Just to clarify. Okie dokie. So last but not least, we have two more. This mechanism right here is pretty important. I believe this is number 13 on our chart. This one's number 12, and this one's number 13. Kind of in reverse order. Why don't we start with this one, just to keep things orderly, and move these down here. Okay, let's talk about this. Take a picture of that. Know it, love it, memorize it, digest it. It's so yummy. Sorry, that was weird. All right, so let's go into this and talk about it. So talking about this one right here, this is our polymerization mechanism. And this polymerization mechanism, what we've seen now, that when we involve peroxides, we're usually going to go into initiation and some kind of other step. We're going to go into the free radical mechanism look and feel of a reaction, and it won't always be like the actual steps of the free radical mechanism. And we're going to see that this one is just insane. It's a never-ending story of free radical mechanisms with this one. This was the one about PVC pipes that I was talking about earlier. So, alrighty. This initiation step is what we start out with. There's only one part of this initiation step. We split up the peroxide. Okay. Using those one-sided arrows. This shows equilibrium, I guess, yeah, I guess equilibrium, and the product going back and forth from the reactant, changing back and forth there. That's not a very scientific way to say it. But anyways, we form our radical here. That's initiation. That's all we need to know. Next comes polymerization. And in this polymerization mechanism, we're going to have as many steps as you want, really. I think we should only go through like 2 or 3 of them, so let's do that. But in this step, you're going to take what you made, this radical over here, and you're going to add it to what we had originally. Oh, here, let's make some more room. There you go. Okay. You have a double bond right there. So this radical here is going to reach out and grab, I don't like that. There you go. Reach out and grab another radical coming off of this double bond, and the other radical electron is going to go to the more substituted position. That is why it goes there. All right. Then that'll form this guy. R connected to O with the radical on the Cl right there. Okay. move this down. So we got this product. Let me draw my electrons there. Then we could take this product, R connected to O, connected to that carbon, which is connected to another carbon with a radical on it, which is connected to a chlorine. And we take that radical and react it with our original alkene in the same fashion, with this radical reaching out. This radical is longer for a reason. It shows the radical actually reaching out there and interacting with the interacting with the double bond. This double bond will split and form another one of these. But instead, it's going to be connected to the first product. So at that point, you get a bunch. And it legitimately just keeps happening over and over and over again. I'll go into just two steps, but it can go like 3, 4, 5, 6, 7, a bunch of times. It's pretty awesome. That's how you get PVC pipes, and that's how it's so cheap to make them. They just keep reacting over and over and over again. All right, but that's that. Okie dokie. So our last but not least, we're going to learn how to take a hydrogen off of an alkyne and be able to slap on another hydrocarbon chain to make our carbon chain longer. This will come in handy in the future. So acid-base chemistry allows us to say that we're going to have this right here. I think, like I said earlier, this is a carbon, that's a carbon, this is a carbon, that's a carbon, and this is a carbon. These blue dots are carbons. Okay. All right. Now these blue dots are carbons. We're going to react it with, also for clarification, when you have Na and NH2, Na is ionic. Naturally, you're going to actually see this like split up into this sort of deal. You're going to see them coupled together in a reaction there, but they're actually going to look like this. So you can just include, you can get rid of the Na part of it, or the sodium part of it, and you can just throw in NH2 there. So, looking at that, this NH2 needs another proton. It's going to grab this, pull off the proton, and throw the electrons back onto this blue carbon right there, forming our second step here, plus NH3. Okay, plus NH3. Now we see in our forming our first product. In our second step, we're going to be adding on bromine with 3 extra carbons onto it. And this will help us to make our carbon chain longer. We're going to see these electrons reach out and basically SN2 reaction backside attack. Let me draw that cooler. Backside attack there, and push off the bromine. And through an SN2 reaction, we're going to get our original alkyne, now with those 3 extra carbons on it. We'll get a bromine ion, and we'll get NH3. And there you go. All right, ladies and gentlemen, that is it for all of the mechanisms from Chapter 8 and with a little bit of Chapter 9 in there. Hopefully that was okay. I think that's 8 mechanisms and 13 different reactions. That is 1 week's worth of material there. Please have fun with that. If you have any questions, email me and I can try to clarify I will post this on an announcement and make a YouTube video out of it. So best of luck. Thank you very much. Love you guys.